Okay, so today I'm talking about parent functions and function transformations. And so I wanted to point out where these things are in the book because that's going to be your best resource here. So in the book, this is in section 6.1. The very first thing is basic functions. So another name for these basic functions are parent functions because all other functions are essentially derived from these initial types of functions. So we've got linear functions and constant functions. So those are two separate types of functions. The identity is basically the parent function where linear functions come from. And then a constant is a special case of the identity functions, basically. So that's basically a line is what we call the identity function. It's called the identity function because whatever number you put in is the same number that you get out. So I zoom in a bit here. So you can see whatever number you put in x, you get out as y or f of x. So your answer is identical to your input. So that's the identity function. And when we do transformations, we use this table to kind of determine the transformations. So scrolling down, we have what is called a quadratic function, which forms what we call parabola. And so that doubles what you put in. And any negatives when you square gets positive. So that's how it forms this U shape. Then we have the cubic function where your exponent is a 3. So this is, we usually always plug in these numbers from -2 to 2, and that helps you form the shape. So you want to be able to recognize what these look like. So you want to be able to memorize the shape that goes with each type of function. Next, we have the square root function. So this one we can't graph square roots of negatives. We can't graph complex numbers or imaginary numbers. So you just start and you pick numbers from x at 0, and then you want to pick numbers that you can take the square root of. So that's how they've chosen these values for the table. And so then it looks like it's going to keep going up. It never flattens out. It just keeps kind of increasing, but slowly. The cubed root function looks like the cube function, but it's kind of flipped over and it's sort of, it's like you tilted it on its side and then reflected it. So these are good points for the cube root function, so you want to be able to recognize that. Then we have the absolute value function, which forms a V. So knowing what it looks like, knowing that an absolute value gives a V. And then what is called the reciprocal function, where you have 1 over a number. So you're taking the reciprocal of what you put in. So if you put in a fraction, it becomes a whole number. If you put in a whole number, it becomes a fraction. And you get a shape like this. So these are the big parent functions, the main shapes of the functions that you want to be able to recognize. You want to be able to see an equation that looks like this and then know, okay, that's what the shape is going to look like. So when we get to transformations, transformations are when we take a parent function and then we do things to it. So I'm going to move over to Desmos. So you start with some function f of x, and I'm going to actually start with x squared, the quadratic parent function, because that's just a nice one where you can really see what's going on. So function transformations are where you do things to x or you do things to y, and it changes the graph. The most common thing we do is add a number to the graph. So if I take my function f of x, and I'm going to create what's called a slider in Desmos. So the slider is just a number, and it allows you to change it so you can see what happens. So this is saying that if I put it positive, if I add 1.1 to my graph, so the original graph, it's at 0, and I can even make this step by whole numbers. So if it's at 0, it's the same as our original graph. But as my a gets bigger, it goes up. So adding a number to the end of your parent function causes this thing to increase. So you would have x squared plus 5. and then your graph is basically shifted up 5. And we can do the same thing. We can go negative, and if you have negative numbers, it makes your graph go down. So this is what's called a vertical shift. It's a transformation, it's a vertical shift. Where adding a number to your function makes it either go up or down from where it was originally. And it doesn't matter what your parent function is. If I change this to the x cubed, so red is the parent function, it still shifts up and down. So the transformations don't care what the original function is. So we can even get rid of the exponent and have a linear function. So I have f of x is x, so this would be x plus a. So if a is 0, I'm not adding anything in. But as I add, you can see it's going up. And then if you subtract it, that's changing your y-intercept, and it's going down. So I'm going to show the absolute value graph. Oops. So you can see we've got the absolute value of x, and adding, it just makes it go up, and then subtracting, it makes it go down. So this is called a vertical transformation. And I will summarize these after I kind of explore it. I want to show you what it does so that you can kind of see visually what's going on, because I think that makes a lot more sense than just trying to look at it and then just look at these equations. So that's one type of transformation where you're adding something to the end here. Another type of transformation is when you're doing it to x. So you're adding and subtracting numbers from x. So normally with x, it's the opposite. So I'm going to just put minus b there, because we usually put minuses. We use the opposite sign with x. I'm going to make sure this counts by 1 just to make it easy. I'm going to start at 0. Oops, that is not 1. There we go. So now I have a slider for b. I'm going to not mess with a. I'm only going to change b. So this is changing what happens to x. So when we see f of x minus b, this is the same thing as having x minus something inside the absolute value. So when you're changing things with x, it's inside your symbol. So here would be inside the absolute value
symbols.
So I'm going to start by moving b to the right. So and this is a minus, so this means as I'm subtracting numbers from b, or subtracting numbers from x, it moves to the right. Now if we go the other direction, if we're subtracting a negative, subtracting negatives is adding, so adding numbers to x makes it go to the left. So this is called a horizontal shift because we're shifting left or right, and it's basically the direction is the opposite of what you see. So if you see a minus with your x, you're actually going to the right. If you see a plus, you're going to a left. So it's the opposite. Yeah, so I'm just making up letters here. There's not really a, if I go back to the book, they summarize the transformations in a table. Goes through all of these things. And they just use A for almost everything here. And then they have some where they use H and K. So don't pay too much attention to the letters. You want to pay attention to the positioning. If it's added on, what happens? Is it inside the X? What happens? So the letters are, I'm just using these so that I'm using A, B, C, just because that way I don't have to reuse them and I can do multiple transformations at the same time. But the letters themselves, what variables you call them, don't matter. It's the positioning that matters here. Where is that number in regards to our function? Yeah, they're just placeholders. That's exactly right. So once I'm going to demonstrate all this with Desmos, and then I'm going to switch to my tablet, and then I'll start showing it with actual numbers so that you can see kind of how it works, and then we'll kind of we'll go back and forth between that and the graph so you can see it. So those are the two types of shifts. We have left or right or up and down. Now we can also multiply the function by something, so that would be putting a number in front. So normally you'd start your multiplying by 1, you're not changing anything. So I'm just make the other two 0. And so if you have your function and you have a number in front of it, so here we'd be multiplying a number in front of the absolute value. So as it goes bigger, what happens is the larger the number is in front, the narrower your shape gets. So as this gets bigger, the shape is getting more narrow from the original, which is in red. And so then as it gets smaller, it gets wider. And when you get numbers less than 1, then it actually becomes wider from the original shape. And it keeps doing that until it gets to a point where once it gets negative, it flips upside down. Yeah, so it inverts it. It basically, we call this a reflection across the x-axis. So we say that it reflects. So if I had -1 in front, it's a perfect reflection from what we have. It's a perfect mirror image. And then it has the same idea where it gets narrower the more negative it gets. If you ignore the negative sign, that number is getting bigger. It gets more negative. And then it kind of widens out as you get closer to numbers to 0. So what this is called is a vertical stretch or shrink. So it's called vertical because it's actually happening to the y values, not the x values. So the x values are not changing. Like you notice the center never moved. It's the y values that are changed. So it's a stretch or a shrink. So we call, when it goes narrower, we call that a stretch, because it's like you're taking the two endpoints and pulling them and stretching them up higher. And when you stretch it, it has to narrow to kind of reach out. So we call that a stretch, but when it goes wider, we call that a shrink, because the numbers are getting smaller. And so it's kind of like you're pushing it down and it gets wider. So if it's wider than the original, it's called a shrink. Otherwise, it's called a stretch. So that's a vertical stretch or shrink, and that happens when you have a number in front. And then that's also called a reflection when it becomes negative. And if I can pick another, if I change this to the square root of x, so we can even see that it's, in this case, wider doesn't really make sense, but it is lower. So you can see it's shrinking. And then it is, you can see, watch kind of the middle part near 0, how it's getting narrower. So that's where you can think of it as it's stretching. It's getting pulled up higher and higher and higher. And then, of course, you can reflect it, and you can see that's where you start getting a mirror image, and then the reflection can go in many different directions. So if I make that back at 0, then, or that should be 1. We've got our original graph here. So these are the 3 basic types of transformations. Usually the stretch and shrink and reflection are considered 2 separate transformations, but they happen with the same number in front. So these are the 3 basic things that occur, and you can have these all happen at any one time. So I could, let's see, A is a vertical, so I could make this go up 2. I could make it go left 3 if I wanted. So I can have both of these going on at the same time. And then if I wanted to reflect it, I can make it a -1 and make it upside down. So any graph that you see is basically one of these transformations that occurred to it. So if I'm going to go back to the textbook, we have these basic shapes, and every graph is made out of these basic shapes, and then they're just moved left, right, up, down, that sort of thing. So they're just shifted around. And that's what transformations are, and there's some pictures that are demonstrating so that it's got this table thing going on. That's what I'm going to do next, just kind of explain how that fits in and how you can do these transformations. So I'm going to, let's just center on, let's do a quadratic. So I'm going to change my screen so that it shares a whiteboard, or at least my tablet, so I can start writing. I'll move my keyboard out of the way so I don't run into it. Okay. And I don't want to accidentally click this. So basic, we have our basic functions, f of x equals x, which is the identity. We have f of x equals x squared. So I'm going to just draw the basic shapes, because that's what you want to know. It's not perfect, but they give you a general idea. So x squared forms a u. F of x equals x cubed forms a shape like that. And then we have, let's see, the square root, which looks something like this. We have f of x, and they have the cubed root, which is harder for me to draw sideways. That was not good. Let me try that again. It's a lot harder for me to draw this one. There we go. Okay, it's better. So that's what the cubed root looks like. We have f of x equals the absolute value of x, so that forms a v when you graph it. And then I'll just squeeze in here the reciprocal, which looks like this, essentially. So those are the basic functions that we're going to be looking at. These are the parent functions. So to summarize our transformations, I'm going to change my variables here just to sort of match with the textbook more. You can do things to a function. You can multiply it by a number in front. You can change x, and you can add numbers at the end. So that value in A, that is the vertical stretch or shrink. And if A is negative or A is less than 0, we have a reflection. So that is a mirror image. It's now below or upside down. X minus h. So that anything that happens to x, that is a horizontal shift. So that moves things left or right, and it does the opposite. I'm going to just write that note. So if you see x minus 2, it moves to the right. If you see x plus 2, it moves to the left. So it does the opposite of what you would think based off of the number that you see. Then k here is our vertical stretch or shift, sorry, not stretch or shrink, vertical shift, which moves it up or down, and that does follow the same sign. So if it's plus, it moves it up. If it's minus, it moves it down. So those are the basic things that happen. Now, when you have reflections, they happen in a certain order, and they actually follow the order of operations. So I'll write that, reflections. I shouldn't say reflections, transformations. Transformations follow the order of operations. And when we transform, we usually do things both to x and to y. And when you do things to x or y, that order doesn't matter because those are separate. So I generally will just do the x first. So I would do my horizontal shift first, left or right. And then when you have the y, you have your vertical stretch or shrink and your vertical shift. So order of operation says that multiplication has to happen first. So when we're graphing these things, we do the vertical stretch or shrink first, and we do the reflection first before you do the vertical shift up or down, because that's the order of operations. Multiplication comes before addition. So the order here, you would be then doing the vertical stretch or shrink. And any reflections. And then you would do your vertical shift up or down. So when you're trying to figure out, oh, what happened to this, if you see a graph and you're trying to figure out, okay, I have this graph, what is it now? How did it move? That's the general order that you would do these. And again, the horizontal shift, because that's not involved with y, that can be done anytime. But the vertical ones have to be done in order where you have the stretch of the shrink first, and then you have reflections. So let's take, I'm going to give us a function. I'm going to call it g. And let's say you have x minus 3 cubed plus 4. So this is our function. If you have something cubed, that's telling us that our parent function is the cube function because that exponent is 3. So our parent function is going to be x cubed, and that tells us what the shape looks like. So you know what it's going to look like. So you go back, you identify your parent function, whether you use the textbook or my little messy notes here. Okay, it has an exponent of 3, so this is what it must look like. And so you've got that parent function, so you know the general shape of what it's going to look like. Next, you need to identify your transformations. So what we have going on here is we're following the same sort of transformations here. So we don't have a number in front that we're multiplied by, so there's no vertical stretch or shrink. But we have x minus h, and here you can see we have x minus 3. So we're subtracting 3. It does the opposite, so this means we are shifting 3 units to the right. This is our horizontal shift. So our graph is going to be moved to the right by 3 from where it originally should be. And then we have this plus 4, so that's added on just like this plus k here. So that is a vertical shift up or down, and since it's plus, it's going to be up. So this means that we shift up 4 units. So that's telling us how this graph has changed. What we have done to our original graph, the parent function, and what it's now, how it's moved to now be this new function. And so then if you want to graph this by hand to understand like how the graphing works and everything, you can look at the table. So I'm going to bring over close, no, just close that whole thing. Okay, so we've got the cube function here and we've got this table. Oh, unfortunately, can I just copy that? Perfect. Okay, so I'm going to just copy and paste that here if it will work. That looks like that's a no. Okay, that did not copy and paste. That's okay, I've got another way to do that. I will take a screenshot. So I'm going to just take a little screenshot of my cubic. Now I'm going to copy that. Oops. In. So this is our parent function, and this is the original ordered pairs for that function. We're going to have different ordered pairs because we have shifted it 3 and 4 in various directions. So these are going to change. So when I do a transformation, I take care of these shifts. So we have our original x values, -2, -1, 0, 1, and 2. And this shift 3 units to the right, that means we're adding 3 to x. So we're adding 3 to those x values. So I'm going to make a new graph or a new table where all of my x values, I've added 3 to them. So if I had -2, I'm adding 3. And then -1 add 3, that's going to be 2, 3, 4, and 5. So now I have different x values. So that horizontal shift is adding 3. And now I called our graph g of x, so I'm going to do that. Label it g of x. A shift up of 4 units means that you're adding 4 to y. So all of those y values on my original table here, I'm going to add 4 to them. So -8 plus 4 is -4. -1 plus 4 is 3. That's going to be 4, 5, 8, 9, 10, 11, 12. And so then I have new ordered pairs that I can graph. Now, the graph here, they're not going to all fit, but I can at least try. So I have 1, -4, 2, 3, 3, 4, 4, 5, and then 5, 12 is going to be like somewhere giant up here. But I'm going to approximate so we can see that it's shifted to the right and it was shifted up. Now, it's not pretty, not a pretty graph, but that's what happened here. So if I bring over Desmos again, I'm going to just turn all of those off and just graph what we have. We have g of x, well as we had x minus 3 cubed plus 4. So actually I can put in, let's do x cubed. So you can see that that actually looks like what I had graphed. Our original graph is in red, and then we moved it to the right and then up 4. So the key is to follow like the middle point here, 0, 0. If I move 0, 0, where it kind of is the center of the graph, I moved it to the right 3 and up 4, you can see it's now the center is right here at 3, 4. So you can see how that moves. So if you follow one key point, you can see that it followed those transformations up to its new location. And so that's, again, my picture is not perfect because I just did, but it's this new point right here, 0, 0, and now it's located up here. And then every other point shifted along with it. So that's one example of getting a new function, identifying the transformations, and then using that to kind of graph it so that you have an idea of what it's going to look like. I'm going to pick another one here. Let's say I have h of x is the absolute value. Actually, let's put -2 in front. Absolute value of x plus 1 minus 4. I already used 4. Let's do minus 3. So new function here. So you identify what the parent function is. We have absolute value symbols, so our parent function is the absolute value function. So that is going to look like a V. So we're going to have a V shape for our graph. So I like to do I like to label all the transformations. So we've got this -2 in front. So we have a reflection because it's negative. And then we have a stretch of 2 because it's a stretch because it's greater than 1. So if the negative means it's going to reflect upside down, and then we're stretching it by 2. What that's going to mean when we start graphing is that we're going to be multiply y by -2. So you're going to be multiplying all your y values by -2. For the x, if it's x plus 1, then we're moving to the left. So we shift left 1, which for x means we're subtracting 1 from x. So all of the x values that we're going to use from our table, you subtract 1 from them. Then we have -3, so that is a vertical shift down. We're going down 3, and that subtracts 3 from y. So I'm going to get back to the textbook, and I'm going to take another screenshot of this absolute value function thing. That's our parent function. So we take that, oops, copy, and I'm going to just paste it right here. So I'm going to be using this table to do my transformations. So I always do the x first. So we're going to be subtracting 1 from all the x values. So the x values they give us start from -1, -2, 0, 1, and 2. I'm going to just subtract 1 from each of those. So that means we're now going from -3 to +1. We just have subtracted 1. Now for the y things, which is the same as f of x, h of x, those are just the same thing as saying y, that's the output. We follow the order of operations, so we do our multiplication first, and then we subtract 3. So we're going to be multiplying y by -2, then subtracting 3 from that answer. So because we're doing multiple things here, I'm actually going to be writing that out. So that way you can see. So we are multiplying the y value that they gave us, 2, by -2, and then I'm going to subtract 3. So I'm going to just write out that math, and then my actual y value once I finish that. So we're going to be at -7. And I'm going to do that for each of these y values. So I multiply it by -2, and then I subtract 3. So 2 minus 3, that's -1. So that one I can actually put on the graph. -3, -7 is going to not fit on my graph. I'm going to have to like guess that it's, oops, somewhere down here. Then, whoops, I actually messed that one up because, let's redo that one. I missed my -2. 1 times, multiply that by -2 minus 3. So it's always good to double check. Okay, -5. So -2, -5. So that's right here. Okay, we had a 0 times -2 minus 3. So it's 0 minus 3. So at -1, I'm now at -3. Then I have 1, I'm multiplying that by -2, then subtracting 3. So -2 minus 3 is -5. Oops. I'm trying to color code here. So 0, -5, so I'm right here. And then my y value is 2, multiply it by -2, subtract 3. So it's -4 minus 3. That gives us -7. So I'm at 1 and then -7. And so you can see that we've still got our V shape. We have our reflection, so you can see that it's upside down. The stretch by 2 made it narrower. That's what a stretch does. So you can see that it's narrower than the original. And then we shifted, if you look at the center point, we shifted it to the left 1 and down 3. So I just kind of look at that middle point for my shifts up and down, just to make sure that that verified that that did what it was supposed to do. So we go left and then down 3. Are there any questions? I'm currently bringing up Alex on another screen so we can do a couple of those. It's just taking a while to load right now. But I definitely recommend, if you're going to print out any part of the textbook, printing out maybe the page with all the transformations or the parent functions would be very helpful. Okay. Just have to get into the student view of Alex. Then once I'm there, okay. So I'm going to just skip to assignments because I haven't done any of them. So of course they're all going to be past due. Okay, so week 5. So graphs of functions. This is the one that where we're doing the transformations and all that kind of stuff. And then there's of course optional ones. I'm actually going to do the optional one because there's going to be a lot more examples there. I know the graphing system here is not the best. Okay, we want function transformations here. What's our x and y intercepts? Domain and range. Okay, perfect. So here's one. It says graph the equation, and you have -2 absolute value of x. So you're going to want to do the same method that we just did. We had the absolute value, and you want to make it. Now here, it's actually almost exactly the same as what we just did, because we have the same thing. We're just not doing anything to x. We're not doing anything to y. So I'm going to, let's do this one. So E, F, G, H, I. Let's make this one J of X. So the Alex problem has -2 times the absolute value of X. So we have the only transformation here is that we're multiplying y by -2. Nothing else is changing. We're not doing anything to X. We're not adding anything on. So I'm going to use this same table. My X values are going to be exactly the same because we're not doing anything to X. Oops. Okay, so I'm going to have -2, -1, 0, 1, and 2. And then all of my y values I'm going to multiply by -2. So those are going to be these y values right here. So 2 times -2 is -4. I'll just call this 1 times -2 is -2. 0 times -2 is 0. 1 times -2 is -2, and then you 2 times -2, which is -4. So you figure out your table, and then that's when you're going to go to Alex. And I'm going to see if I can do this side by side. Okay. So I would use this button right here because this is where you can plot points so that you can get it more exact. So you can actually type in the values that you want. So -2 and -4. So see, it's plotting that point, and you click plot point, and you can just do this for as many of the points that you want. So I'm going to just do this for all of them. -4. So I plotted the points, but we don't want just those points because we need to connect them with a line. Let's see if I can get the X. So I don't want this line. Well, I could actually. Yeah, this looks like this could work. What does this one do? Okay, so we definitely don't want this line because that's going to go too far. So we want this one here. So I'm going to click here, and then I'm going to click one of my other points that I have. And you can see it's kind of snapping to grid. So it's snapping, and it highlights when I'm on the point, so you can make sure that you're on the right spot. It's hard to see, but it kind of turned yellow there. So then I can click, and then I have that line. And then here, again, I'm going to start in the middle, and now I'm going to match it up, and then that gives me my other one, and then I can check it. And there you go. So that's how you want to graph in Alex. I strongly recommend using this tool here because that will make sure you have your points in the right place, so that's a lot easier to try to match them. And it should work the same whether you have a parabola or anything else. Let me see if I can find a... So for an x cubed, they give you a curve. So you need to plot your points first and then use the curve to follow those points. So that will make this a lot easier for you, is to make sure you have those points. And that's how you get those points, is from those tables that we were doing before. Let's see if there's anything. All of these are requiring you to plot 5 points, which is just good practice. They are giving you some directions on some of these, like making sure you plot where your y value is going to be equal to 0 here, and then it says pick 2 to the left and 2 to the right. Now, generally, let's see. So let's do a problem like this, because this is a good one to do. So we've got the cubed root of x minus 4. So I'll just do this on the side here. Cubed root of x minus 4. So going back to the textbook, I'm going to take a little screenshot of for cubed roots, so we know what we're looking at here. Let me just paste it right there. So that's going to be the general shape. And the only transformation we have is that -4. So it means all of the x values here are not changing, but we are subtracting 4 from each of the y's. That's the only transformation we have here. So this is going down 4, just subtract 4 from y. So my x and I haven't done anything to x, so all of my x values are the same. And I'm going to subtract 4 from each of these y values. So -2 minus 4 is -6. -1 minus 4 is -5. That's -4. -3, 2 minus 4 is -2. So now I'm going to go back to Alex. So it says, it gives us some specific directions here. Plot the first point using the x value that satisfies where is this equation equal to 0. So it's saying where is cubed root of x equal to 0. That is what it's talking about, this point right here, where your function f of x is equal to 0, and that corresponds with this transformation point. So that's what that's saying, is it's specifying that you need to make sure you include this point. And the way that we're graphing these already fits that requirement. So I know that I'm going to have 0, -4. So I'll make sure to plot that point. So I plotted it right there. Now it also says plot 2 points to the left and 2 points to the right of that first point. So we've actually got that right here. I have 2 to the left and then 2 to the right. So I can just use my plot a point here to enter in these other points. Assuming that I did all of my math right. 1, 3, 2. Okay, I'm going to close that. So now we're going to do the curve. So the nice thing is it actually tries to fill it in for you already for something like this. Unlike with the absolute value where we had to create it, here it actually already filled in. It's just up to you to make sure that your points are correct. And then we don't have to do anything. It already connected them all. So that's how graphing works. It's a lot easier than earlier when we had the graphing and you had to eyeball the points. The graphing here is actually pretty smart. Here's a good one. So translate it to make this graph. So we have x -5 squared plus 1. So the -5 means we're moving to the right 5. So I'm going to take this middle point and move it to the right 5. And then we have a transformation of +1, which means it goes up 1. So I'm just going to click and drag and move it up 1. So you're working on that middle point and you're moving it following our transformation rules to do a transformation. So for something like this, you're just following this and it's already graphed for you. So all you care about is moving 1 point. Let's see, what else do we have? Okay, this is understanding the values, whether it's going to be a negative coefficient or a positive coefficient. Is it going to be greater than 1, which makes it narrower? Is it smaller than 1, which makes it flatter? Those kind of things. So I think pretty much we've gone over. This is good too. So people struggle with these kind as well. So we've got the graph of f of x, and it's not one of our normal graphs. Draw the graph of negative f of x. So that's going to be a reflection. So again, I like to determine key points on here. So if they don't give you a table, you can make a table just by reading the graph. And then you can transform those. So here we're just doing a negative in front of x. So I'm going to have, I don't know if I want to eyeball it because I might not get it quite right. So like we have 0, 0, but if we need to make it, let's see, that negative multiplies the y value by negative, so that's going to stay in the same place. And then we have this point 2, negative 2. So that negative in front of the f of x is only changing the y. So it's still going to be at 2. It was negative 2. We're going to be multiplying by a negative 1, so now it's a positive 2. Then let's take this point 4, 0, 4, or 4, comma 0. That's going to stay in the same spot because when you multiply the y value by a negative 1, it's still 0. And then let's take, let's say we have the 7, 3 point right here. The 7 is not going to change. We're not doing anything to x. Oops. And we're multiplying the y value by negative 1. So instead of being up at 3, it's going to be negative 3. So when you're given an unusual shape, you're going to want to use the key points. Try to use enough points that you can get the right shape. So if you want endpoints where it changes direction, that sort of thing. And then we're going to connect them. And so that way, now I've just drawn, and you can verify that it's a reflection. Now, one thing I didn't talk about is graphs like this, where you have a negative in front of x. So instead of shifting x left or right, it's multiplying by x by a negative. So it's just going to be a mirror image, but across the y-axis instead of the x-axis. So if an x value is here, it's now going to be over here. If it's over here, it's now going to be over there. So that's the kind of transformation and you could, again, you can just pick, in this case, it's just a line, so we can just pick these 2 points. So let's do this one. Well, it would help if I could actually see the graph. So we have, let's see, negative 4, comma, negative 5. So if I'm multiplying my x by negative, that's now going to be positive 4, negative 5. Now this other point down here is 4, comma, negative 7. So it's going to now be negative 4 because we're multiplying x by negative, and then negative 7. And then that's enough for me to get the shape. And so that forms a reflection. It's just across the vertical instead of a horizontal reflection. So that's the idea of function transformations, showing you how to do this stuff in ALEX. Do you guys have any questions? Okay. Well, hopefully this made sense to you. I know that reading function transformations, usually, like at least for me, when I'm reading and I'm like, what's going on? I like to see a visual, you know, and actually see how things are moving, kind of watch the process. I think it makes a lot more sense. So yeah, so thank you guys for joining. I appreciate it. I hope you guys have had a great weekend so far. And I will get this out tomorrow morning. I will definitely send a PDF of the OneNote that I created. I think there's definitely a document in the classroom already with like a summary of the function transformations, but I will send this one out as well so that you have that. And I hope you guys have a great night. So I'll talk to you guys later.